Conformation. Conformations. We left off drawing. Any questions before we get started about conformation? How we do on the other two? Let's draw the one in the middle. Everybody can see this in the back? One in the middle. Newman conformation. Which is the best Newman conformation? We'll start by drawing what we see in a Newman conformation. Here's the molecule. Backbone. Backbone is in the plane. Carbon is in black. Second carbon, we have a bromine. The bromine is coming towards you guys. It's bold. Towards you guys. Carbon over here. Methyl going back. That's a methyl. That's just to a carbon. That's to a methyl. Going back. The ethyl is coming straight down and then straight in the plane of the board. Although we're not going to worry about this. This can rotate. We're not worried about it because we're looking down the 2-3 bond. You see the nomenclature, this is 2-3. We're going to be looking down 2-3 bond. 2-3. So I'm looking down the 2-3 bond. 2-3. 2 in the front and 3 in the back. I'm over here. I could turn the molecule and we could all look down it. Problem is I can't turn the board. So now you could actually turn your paper if you got it. Sometimes you'll see me doing this. You could do that. I can't turn the board. Because of that, I've got to stand over here. Act like I can't turn the model. Gee, I just can't turn the model. So how am I going to look down the 2-3 bond with 2 being in front? Well, guess what? I've got to come over here, and now I can look down the 2-3 bond. All right? So I've got to stand like the little guy like this. I'm just going to take this off and move the board forward. Kind of like here's the board. Okay? That's what I'm seeing there. All right, what do I see? I see the front carbon. This is a 2 carbon. 2, 3. 2 carbon. What do I see on the 2? I see a methyl coming straight down my feet. I'm drawing what I see. I wish I had a board right here. I could draw it and then turn it and let you see. But pretend I'm drawing what I see. I'm drawing what I see, but I'm this way. Front carbon, I see a methyl straight down. I'm going to draw it in as an ME because I like to clarify just the line. Methyls. I see a bromine. It's going towards you guys. If I'm over here, the bromine's going to the right, to my right. So I see a bromine to the right. It's also coming up a little bit. Bromine to the right, up a little bit. Over here, what's going back on that carbon? What's going back on carbon 2? An androne hydrogen. Little guy right here. To my left, going behind the board. I see an H to my left. I see an H to my left. Now let's look past carbon 2 back to carbon 3. What do I see back on carbon 3? What's going straight down? The carbon, it's got an ethyl. It could have 10 carbons attached, but it's going straight down, and the rest we don't worry about. We're just worried about these two, this bond. Ethyl going straight down. Hold on, this got turned. Ethyl going straight down. We got a methyl going straight down the front. Well, look, the methyl and the ethyl are eclipsed. You see how they're eclipsed? They are, as drawn. The ethyl's coming straight down. It's eclipsed with the methyl. The methyl's in front. Okay? Carbon 3, I got an H towards you guys. Because if it was drawn in, it would be bolded. Tetrahedral, 2 in the plane, 1 forward, 1 back. The H would be bolded. There it is. It's coming towards you guys. It's actually eclipsing with the bromine. See how it's eclipsing with the bromine? That's supposed to be right behind it, but that's the way we do it. We can't draw right behind it. What's on carbon 3 going behind the board? The methyl group, right? If I'm over here, it's to my left. There it is as drawn in a Newman conformation. Is that the best conformation for the compound? No. What's the high priority group or the biggest group on the first carbon? Bromine, methyl, H. It's going to be bromine. That's a huge atom. Now, books will give you tables where you can look up steric values for this. Sterics mean the crowding values, or the size, demand for the different. Bromine typically is going to have a bigger steric demand than a methyl. We'll try to make it clear here. Typically, bigger the halogen, bigger the steric demand, although that does slightly vary a little bit for us. Bromine is more demanding than chlorine. Alkyl groups, ethyl is bigger than methyl. That should make sense. Just more carbons. A T-butyl would be bigger, more substitution. We come from examples and asking questions. Biggest group on the back carbon, H, methyl, or ethyl? Ethyl. Ethyl is bigger than methyl. Okay, are those two groups currently anti? No, we want biggest groups anti. We can rotate either one. I'll rotate the front. The ethyl's here. I want the bromine to be here. Rotate. Front carbon, we now have the bromine straight up. I'm just turning this. Bromine goes straight up. The H is going to come here. And the methyl then swings a little bit here. The back we did not move. We have an H here, a methyl here. Don't get your methyls mixed up. You have a methyl on the front carbon, you have a methyl on the second carbon, back carbon. And then what's here? This is the ethyl, yeah? Okay, now your two high priority groups, or biggest groups, are anti, and that's the best conformation. That's where we took the original they're on the board, bromine forward, methyl back. Here it is as a Newman. Everybody agree that that's the Newman? Front carbon. Bromine to the right, H to the left, methyl straight down. Back carbon, ethyl straight down off of that back carbon. H eclipsing the bromine, methyl eclipsing the H. What did we do? We rotated the front to where? Just to right there. And now we have the best conformation because the bromine and the ethyl are anti. The bromine and the ethyl are anti. That's the best conformation. Now, why is that important? Well, this molecule has free rotation all over the place. The question is, first off, can you draw it in a Newman? That's just part of, can you do this? Then, at any given moment, what's going to be the most favored? Any one? Or is it going to want to gravitate towards this sort of being opposite? Again, this thing's nervous sitting there. It's rotating. It's energy. But if at any given time, is this going to be up like this, or is it going to be more down like this? It's going to be more anti at any given time. Is it always just like that in stuff? No, it's got some movement. We're showing the best. Boom, there it is. Again, we got the bromine up and down. That's it. Then we can ask questions, okay? I mean, this H and this bromine are doused to each other, yeah? And the best conformation, the two hydrogens are anti to each other. Everybody agree? Two hydrogens are anti? I mean, now we can describe it. We can talk about it using terminology. How do we do on that one? Please try the next one on your own based on, see if you can do it now if you weren't able to do it beforehand. Questions? Can a center gauge conformation sometimes be preferred over an anti? Yeah, if you look at this compound here, the two OH groups are your bigger groups. They're not anti. This is actually preferred conformation. The two OH groups are gauche. Why is it not anti in this case? This is an exception. There's plenty of exceptions. Why do these two want to be gauche instead of anti? What do we have here?
H bonding.
Intramolecular hydrogen bonding. Now, hydrogen bond is not a full covalent bond, but it's like a pinky bond. It's not a covalent bond, but it's an interaction which is a good thing. If it wasn't good, we wouldn't be talking about it and how much it does. It's like it holds DNA together. It's a good thing. That's why it holds DNA together. But it's holding these two groups gauche to each other when maybe the opening comment would be they expect them to be anti. So, can you understand why this is an exception? There's often exceptions to the opening statement. Make sense? So these groups, if the two OH groups, instead of being anti, they're like, whoa, okay, I'll interact with you, boop, and make a hydrogen bond. Okay, is intermolecular H bonding possible in the following compound? Yes. Do you have to show such always in a Newman? No, we could show this otherwise. We could show this like maybe something like this. What can hydrogen bond to each other? How would you show this? What's hydrogen bonding to each other? Is the O-long pair going to be involved in hydrogen bonding, intramolecular hydrogen bonding? What would the hydrogen bond do? It ain't going to hydrogen bond to the H, it's already covalently bonded to it. It might hydrogen bond to the H of another molecule, but that would be intermolecular. We're looking at intramolecular. No. Hydrogen bonding is going to come between, this is your H bond donor, the H here. What's going to be the accept? Which nitrogen is going to be the acceptor? This one. Why?
Closer.
Yeah. We have a tough time hydrogen bonding over here intramolecularly. Can we show that? Boom. One carbon, two carbons, and then an OH. I just rotated that bond right there. The O is down. I rotate it up. Just like I rotate my arm. Now, what do we have here? A beautiful intramolecular hydrogen bond. So how's this bond going to sort of want to be rotated? You know, going to be rotated with the OH away, or do you envision that most of the time it's going to be rotated with the OH up? Yeah. I mean, did we have to draw it in a Newman to see this? No. You can draw these like that. Make sense? yes, it'd have a hard time hydrogen bonding over here. Typically, in these intramolecular hydrogen bondings, 5 and 6 is your best pseudo ring. 1, 2, 3, 4, 5, 6. Okay? Just like slapping hands here. The best is sort of this length. If my other arm was twice as long, okay, like this, I go to slap hands and I'm like, uh-oh, my arm's too long. But as is, boom, I have the right size. Okay? It don't work. That ain't going to be able to come over here. Okay, yes, it's close. I need to be able to go backwards. I can see that back there. No? You can't see, yell. Because I can't see. I don't know why it's not showing up. They changed the bulb in this thing. I don't know if that would matter to put some type of new bulb in it or. Okay, need to be able to go backwards for Newman projections here. Back to a more conventional line bond. In doing this, we could worry about the perspective, the dash and the bold orientation. You really don't have to do this at this time. So I'm not going to do it. Maybe later on you would need to do it, but for now, let's just get the connectivity there. I got a front carbon and a back carbon, yeah? What's on the front carbon? I got a methyl, a bromine, and what else?
Butyl.
A butyl. 1, 2, 3, 4. How about that? Yeah? Back carbon, what do I have? An F and 2 H's? How about if I just make that a CH2F? Again, I don't have to worry about the perspective, the dash and the bold here. I'm not doing that because we really don't need to do it to get a name because we haven't covered that much yet. I can clean this up and make it a nice line bond. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5. And then the fifth carbon has a bromine and a methyl. And then the next carbon is a CH2 and then an F. Sort of clean it up a little bit. There's our compound. Everybody there? Yeah? And now you can just name the compound. Which that was the task. Name these compounds. What do we have here? 1, 2, 3, 4, 5, 6. Or 1, 2, 3, 4, 5, 6. 1, 2, 3, 1, 2, 3, 4, 5, 6. Which is 1, here or here? One, 2, 3, 4, 5, 6. That would have 2 substituents. If that was 1, 2, how many substituents on that? 3, 4, 5, 6. It'd be 3 substituents. So that's it, 1 to 6. More substituents, right? If that was number 1, you'd only have 2 substituents. So we're going to make that number 1. 1, 2, 3, 4, 5, 6. What is that, a hexane? What's on the hexane? Fluoro, bromo, and methyl. Alphabetical order. What's that, bromo? 2 bromo. So we got 1 fluoro. UORO. 2 methyl hexane. Does that look right? Again, we did not do any stereochemistry. We don't know how to name stereochemistry anyway. So when I came back here, I didn't do dashed or bold for any of these groups. We could start with that. I showed you how to do that, but okay. We don't know how to go backwards yet. Try the other one on your own. Cyclohexanes, chair conformations. Let's go back a little bit though. Overview of cycloalkanes. Ringed alkane, cycloalkane. The smallest ringed alkane you can have is cyclopropane. Cyclopropane. Cyclobutane, etc. We'll be looking at cyclohexanes and drawing the chair conformation. You can have larger. Some comments about these first. First off, the first two have ring strain, so-called angle strain. These are less stable. Ring strain. For ninth grade geometry, what's that bond angle?
60 degrees.
60 degrees? But that's a tetrahedral carbon. Each carbon has two H's, right? An alkane, there's two H's there. It's tetrahedral. Tetrahedral wants to be 109.5. Is it happy being 60? No. Huge deviations from normal is not happy. That's not good. Normal means that's the best. I mean, you can have small deviation. That's a huge deviation. What is this? 90 degrees. Not as bad, but that's still some deviation from normal. Normal being the ideal. Okay? I don't have it here, but if you want to make ring bonds, that's 109.5. It's a tetrahedral. If I want to make it 60, I've got to go. There you go. And make it 60. That takes a lot of energy to do that, just like my fingers have to do this. Boing. There's a lot of potential energy there. That's why it goes boing. All right? That leads to so-called ring strain, angle strain, bond strain. First two have it. They're less stable than the others. Does this mean that you cannot have such a ring? No, you see this ring a good bit. Because there's more to the story than this. There is strain there, but it's mainly relative to these. 5 and 6 are your best size rings. Why? Because this is more closer to 109.5. 5 and 6 are your best rings. What about larger rings? They're possible. They're actually not as good as 5 or 6 because, for example, maybe this is ideal, 109.5. 60, I have to push it in. Bigger rings actually require bigger bond angles. Because if everyone was 109.5, you wouldn't be able to get but 5 or 6 in the ring. So you've got to stretch it open to get more in the ring. And the stretching open is also bad, just like compressing it together is bad. 5 and 6 are your best. That's a general statement. How do we know how bad these are and that they're bad? We can look at heats of formation. Don't worry about these over here, okay? Heats of formation. You need to know what that means. The heats of formation for the first two, cyclopropane and butane, are actually positive. Okay, Cal. Positive. The remainder are negative. Now, heat of formation is the heat it takes to make a compound from the elements. So that is, you take carbon and you take hydrogen and you make like cyclopropane. If you do that, you have to put in heat. This much, because it's positive, right? Positive means it's endothermic. Okay. This is a delta H. Okay. Endothermic. Now, typically, when you start making covalent bonds from the elements, that's typically a good thing, and it typically is exothermic. And indeed, it is exothermic for the other ones, especially the 5 and 6. When you make those from the elements, you get off heat. Why do you have to put in heat to make the first two? You have to put in energy to compress the bonds. So the fact that these have high energy is seen right here. Now what can be confusing is I told you that the bigger ones were unstable. Why are they exothermic? Well, that's because you got apples and oranges here. Yes, you do have broader bonds, but you also have a lot more carbon-carbon bonds. And so, for example, you see how these go up, more carbon bonds, but this one doesn't continue to go up. Because it's being hurt by the fact that the bonds are wide. So a little bit misleading, but you can certainly see it here. These are endothermic because of ring strength. Heats of formation. Heats of formation. If you're going to build something that has high energy bonds, you're going to have to put energy in. Okay, we're going to focus on cyclohexanes a little bit. Let's look at disubstituted. Now, monosubstituted, pretty easy. Okay, let's just look at that. That would be called methyl cyclohexane. You don't even need the one because there's only one thing there, and the one group is at the one position by default. If this was a bromine, it would be bromocyclohexane. Let's look at disubstituted though. Here's where we can have the potential for isomers. You could have 1,2-dimethyl cyclohexane, yeah? But this would be what? This would be 1,3-dimethyl cyclohexane, and this one would be 1,4-dimethyl cyclohexane. The relationship between these three, they're isomers. They have the same formula. What type of isomers? Constitutional isomers. Same formula, different connectivity. Here the methyls are connected at the 1,2 position. Here the methyls are connected at the 1 and 4. Different connectivity, constitutional isomers. Is there another one? Is there another constitutional isomer possible for dimethyl cyclohexane? Is there another constitutional isomer possible for dimethyl cyclohexane? You see it? What is it? Yes! Very good. How about 1,1-dimethyl cyclohexane with two methyls in the same position? I'm not showing that one, am I? 2,2-dimethyl? No such thing. No such thing as 2,2. That'd be called 1,1. Right, okay. But these are three because we look at the different positioning. That's what I'm really looking at here. Let's look at this a little bit deeper here. Let's take the 1,2. The two methyl groups could be both projected forward. Or they can both be projected back. These are tetrahedral. Two in the plane, one forward, one back. The back being here is hydrogen, right? We don't draw in the hydrogens, but if you did, they would be back, right? Here it's just the two H's are forward. The methyls are back. Terminology. These are both called cis. When the groups are the same direction, that's called cis. We can also have trans. One forward, one back. You can also have maybe one back, one forward. variation of that. It's also trans. What's the relationship between, well, hold on, let's be careful. First off, as we'll learn during test 2, these two are actually the same compound. So I can't ask you what's the relationship. They're the same. It's one compound. Over here I can though. These are different compounds. We'll learn that during test 2 when we do stereochemistry. They're different. What's the relationship between these two different compounds? Are they constitutional isomers? They are not. They're both 1,2-dimethyl cyclohexane. They're both connected at the 1 and 2. The difference is how they're projected. And when the difference is only how they're projected, you're looking at stereochemistry. Okay? And these are known as not constitutional isomers, but stereoisomers. Difference in projections. Same connectivity. Same exact name. More later, test 2. And that is total of 3 stereoisomers. 1, 2, and that's the same compound, so that's 3. It's just drawn twice. Okay, cyclopropanes, I told you do see them. There's actually a large number of drugs with cyclopropanes, like Cipro. Okay. Amazing number. I'm actually interested in kind of writing something about this for publishing, because I've never seen it discussed of how many there are, and like cataloging them and maybe giving some rationale, pulling together some literature to talk about why potentially there's lots of them. And I've got a whole list of compounds organized. I got to find someone to help me do that at some point. There's also some drugs down here with cyclohexanes, such as number 6 here, gabapentin, anticonvulsant compound here. It's a pretty simple compound. It's just a cyclohexane with 2 groups at the 1 position. Very important drug though. There's some information down there about cyclopropanes. Let's look at drawing cyclohexane. Back over on the other sheet. I've got a cyclohexane here. 2 groups. A lot of times it's just a single, like halogens, a single group here and a single group here. 1-2 positioning. Okay. Because every atom of the ring is tetrahedral, this ring is not flat. Not flat. We'll look at that. On the other hand, a benzene ring where every atom has a p orbital and thus is trigonal planar, because every atom is planar, and they have to line up with the p orbitals overlapping, keeping every atom planar, the whole molecule ends up being planar, the whole ring. So it's flat like a plane. Benzene ring. All right, you'll see more of that in organic 2. Here, the cyclohexane is not flat. Okay, if you want to flatten it out, you got to pull this down and pull this up and flatten it out. You can do it by your hand. Now it's flat. But if it's flat, first off, let's look. Let's look down a bond if it is flat. What are the hydrogens doing if it's flat? What are they doing if it's flat? They're eclipsing. Everybody see it? Okay. If it's flat, the adjacent hydrogens are eclipsing. Is that good? No. Also, if they're flat, the bonds have to be bigger than 109.5. Look at that bond, how it's bowed out. Do you see how it's bowed? Even in my model, it's bowed out because I made it like this. Okay? That'll do it because my bonds here are a little stretchy. But if we flip one end up and another end down, we can do that because we have a little bit of movement. Now let's look at adjacent hydrogens. Okay, over here. Are they eclipsing? Here's the back H. Is there one straight up in the front? They're no longer eclipsing. All right? That H is no longer eclipsing. Now the bond angles, they're no longer bowed. The bond angles are better. Okay? All right? Just take that into if you can't see. And what I did here is I went not flat, but I moved to what's called a chair conformation. Because this is flat, and then you got kind of a back where the back of your chair, and then you got sort of a leg rest that's spilling over. You can see this in your book better. All right? Because what I did is I flipped one end up and the other went down. I could have also flipped both ends up. Both ends up is called a boat conformation. That's not good, and we're never going to look at it again because in a boat conformation, two groups at the top up here, they become too close. Okay? That's called flagpole interactions. Yeah. So instead of one end goes up, the other end goes down. And that is your classical chair conformation, and that's the best. Okay? That's how cyclohexanes typically exist. Not flat. The benzene, on the other hand, flat. It has to be for various reasons. What we want to do is, can we show this on the board? Okay? Now, when we draw a cyclohexane, yeah, we draw it like that. Looks flat. This is a limited view. We want to look at it a little bit closer. We know it's not flat. How do we draw this on the board? Here we go. Start with two lines like this. Horizontal. Offset a little bit. We'll do this a few times. That's actually already 4 carbons on the board. 1, 2, 3, 4. We're just going to connect this here with 1 carbon, and then we're going to connect this here with another carbon. Did your textbook take you through how to draw these? Yeah? Okay, there it is. Now, here at the bottom, this is supposed to be sort of a little bit in front of that back there. All right, not completely flat, but now this end is up, this end point is down, which my model was a lot bigger. But this line over here is sort of in front of that back there. All right, importantly, how do you draw on the H's? We have 3 carbons that I call up. Boom, boom, and boom. These are up carbons. These get straight up bonds. All right? And if we're doing H's, we're going to have straight up H's. And this one's sort of right there. Again, it's more sort of in front of that back there. Straight up carbons get straight up bonds. Straight down carbons get straight down bonds. There is 2 H's on each carbon. Now over here, if we drew in the H's, we might draw one back and one forward, right? You could do that on every carbon. That's called a standard perspective drawing. This is our chair conformation, or more of a conformation drawing. All right. Each carbon needs one more H. The other H, okay, straight up carbon, straight up H. The other H, by the way, before we go on, all those H's are called axial. Now I can make these red and the others blue, but I guarantee you don't have different inks, so I'm not going to do it either. All right? I didn't tell you to bring different ink today. Those in blue are called axial. Now the other ones in blue are going to be called equatorial. These are the non-straight up or straight down. This one goes here. It goes parallel, not to the carbon bonds that are there connected to that carbon, but the one next. This bond is parallel to this, or that. See how that's parallel to that? Okay. And these are going to be called equatorial. Equator. Around the equator. Not up or down like the poles, but equatorial. That is, you got some straight up, some straight down, and you got some that are sticking out around the side. Those are equatorial. How do you draw this one in? Not parallel to the connected bonds, parallel to the next bond. So it's going to be parallel to that, so it's coming up a little bit. All right? Yeah? Not parallel to the connecting bonds, but one over, parallel to that. One over this way or one over that way. This is parallel to these two. You draw that one there. Boom. Now it doesn't have to be always exactly. That's supposed to be parallel to that. It's not quite, but it's close enough. Yeah. This one. Everything goes to the outer. Okay, so nothing's going to come into the internal into this. It goes outer. It goes sort of like that. Parallel to this. And there we have, what's the formula for this? C6 what? H12, right? 1 DUS, because we have one ring. So we drew in our 12 hydrogens, yeah? 6 of them axial, 6 of them equatorial. If I take these off, if I take this chair conformation and sit it down, how many H's are touching the table? I know you guys can see better. 3. Those are the 3 axial hydrogens going straight down. Turn it over, how many are touching the table? 3. Those are the 3 that we're now going down, but before we're going straight up. The other 6 will never touch the table. Those are to the side, or gosh, they're equatorial. Okay, it's coming around the equator. They're not like the poles. All right. Now, let's see what we're going to do. We need to kind of move. We're going to do ring flip. We can go ahead and make some statements. The best positioning is for groups. If we start putting groups on here, the best position is equatorial. Okay? There's more room equatorial. The axial positions do interact with the other axial positions, and that's a little bit not good. That's called a 1-3 diaxial interaction. The 1-3 diaxial interactions make the axial positions not as good. Take home is equatorial is your best position. Now let's star this hydrogen right here. Okay? Now one thing that's often done is a ring flip. That is, this thing can flip back and forth. This can come down and this can go up. Now this end is down and this end is up. We need to be able to draw that. This one I started drawing lines like this. To do the ring flip, we're going to do just the opposite. We're going to do sort of mirroring. Not like we did originally. Then we're going to connect like this, and then we're going to connect, this is a little bit too long, like that. I'm going to change this to 1 and change this to 2. Let's keep track of those hydrogens and let's find them over here when we're done. Okay, first off, these are straight up, right? Straight up and straight up. These are straight down, straight down, straight down. Yeah? You can draw these on your own. Boom, boom. This has got to be parallel to that. This is going to be parallel to that. This is going to be parallel to this. Okay. This is where this end was pulled down, and this end was pulled up. Where's hydrogen 1 and 2 now? Hydrogen 1, anybody got it? Here? Which one's hydrogen 1? That one right there is hydrogen 1. I pulled this end down. That's it. Where's hydrogen 2? Well, that's 1. Hydrogen 2 is on the next carbon, right? It's on the next carbon. And it is, which one of these? It's this one right here. Very important here. Whenever you do a ring flip, all axials go to equatorial. Axial here, it's now equatorial. I can prove that over here. Here's a chair conformation of this compound with a substituent. The substituent is currently axial. Everybody agree? Let's do a ring flip. Okay? From one chair to the other. Now your book will take you through, like this is a partial something, and then no, we're just going from one to the other. This up, this down. Okay? Now how's the group? Now it's equatorial. All right? We set it down, it will never touch the desk now. It's equatorial. Anytime you do a ring flip, your axials go to equatorial, your equatorials go to axial. Axial, equatorial. Equatorial, now it's what, as expected? Axial. That's important for doing ring flips. Question? No question. Last thing, guys, then you can look ahead. These two groups right here. Two groups. Are they cis or trans to each other? Okay? Now, if I did it right here, these two H's are what to each other? Cis. We showed that. Okay? But can you tell from here? It's not to be meant the same. I don't know if the answer is the same or not. Two separate things. What's the relation between those two groups, cis or trans? And we'll end here. Cis or trans? You want to draw it like this until? Those groups are trans. If I had drawn this ring like this, they would be trans. Okay? Why is that? Last statement. I'm giving you take-home statements at this point because we're near the end. Compare the two H's. This one is below compared to that H. It's down compared to that H. It's lower on the board compared to that H. It's down compared to the H. We're not talking about axial or equatorial. How is this one compared to the other H? Up. That one's down compared to the H. This one's up compared to the H. They're opposite. Opposites called trans. Have a good week, guys. We'll pick this up. We'll finish this up on Wednesday. We'll pull in loose ends on Wednesday. See what types of questions you have. Maybe look at IR. Friday, definitely, we're starting new material. Test 2 material. Have a good day, guys. Please be looking ahead, trying these problems. We'll do them on Wednesday. Biggest groups, equatorial.